Welcome to CS110 Lab number 5 video recording. I'll be taking you through the content of lab number 5 over here. This version of the lab video is intended to be used along with our Replit teams. For lab 5, there are 3 projects that you can work with. The first one is for the main lab exercises. Specific instructions to this semester's version of the lab are found in there if you click Start Project. During my lab lecture, I may make reference to extra stuff to help you understand Boolean expressions, one of the more complicated things we introduced this week. Boolean expressions will also be important to you in lab number 6 and later on in the semester. They are fundamental to computer science. So I've got a Boolean practice that I will probably be going through, and you should try to understand everything that's going on in there as well. The last piece here, Lab 5 Extra number 2, is something I sometimes offer for bonus marks to people who have more time than have time left over at the end of the exercise in lab. So let's get into what's in the lab notes. My goals for all of you today are to be able to form a correct Boolean expression. A Boolean expression is a mathematical expression that uses operators that work a little bit like add, subtract, multiply, and divide, but produce results that are only true or false and expect inputs that are originally only true or false. So we'll be learning how to create trues and falses from the data types that you already know for use in these Boolean expressions. These trues and falses then are used to help your programs to make decisions about what to do next. So we'll be building up our ability to make decisions, and with those decisions we can either choose to do one thing, or maybe choose between doing 2 different things, or decide whether or not we're going to loop through a piece of code again. We're going to help you to understand how to read and evaluate a Boolean expression correctly so that you know what is likely to happen when you get to one in your code, and so that you can read code and understand your own code as you're writing it and not be confused about it. We're going to also learn the syntax of if statements, and we're going to learn how to put our Boolean expressions into our if statements to help make the choices that we want. Exercises 1 and 2 will be required in lab, I think always, and the bouncing ball exercise is typically offered as a bonus, though not always. You should ask your lab instructor whether you're going to do the bouncing ball exercise or whether they wish to offer it as a bonus. So we're going to go into Boolean type and Boolean expressions. Now, all computers are based basically on only true and false values. At their lowest level, all instructions in a computer, all values stored by a computer are made up of 1s and 0s. The 1s and 0s represent true for a 1 and 0 for a false. And at the most basic level, computers make decisions based on these trues and falses. When we want to make a decision in our programs, we can put together a lot of complicated information, but the computer really only can make a choice about what to do next when a choice is offered, if we can boil down our complicated thing to a true or a false. In C++, if we want to talk about one true or one false at a time, we use the special data type bool. Bool can be declared in your programs just like int or string or float. It's an example of an integer data type with only 2 values. You can semantically write those values as true or false. If you put something else instead of a true or a false where a bool would normally be expected, then anything that is non-zero will be turned into the number 1 and will be considered true. Anything that is equivalent to 0 will become false. So if you accidentally type an integer or a float or a string somewhere that a Boolean expression is expected, a true or a false value, it will be coerced into being true or false, and you might get unexpected results. So you need to be careful that you're actually forming a correct Boolean expression when decisions need to be made. To help you to turn the data types you're already familiar with into Boolean values, we can use relational operators. Relational operators compare 2 different values. They don't need to be the same type, so long as they can be converted into something similar to each other, kind of like a float could become an integer by losing some information, or an integer could be stored in a float. You can compare a float and an int most of the time. You may have some loss of precision or accuracy if you do that. Boolean expressions usually require a relational operator to be used as one of the first steps. So you can compare two different values. We refer to one side of the value as the left-hand side and the other side as the right-hand side. The first relational operator is the equal to relational operator. The equal to relational operator is true if the left-hand side and the right-hand side are considered equal to each other after they've been converted into the same data type. The result will be a true Boolean value if they are equal, and a false Boolean value if, after all conversions, they are not equal to each other. The not equal to symbol is similar to the equal to symbol. Notice the equal to symbol has two equal signs. Be careful not to use just one. That will assign the right-hand side to the left. The not equal sign to symbol replaces the first equal with an exclamation mark. In C++, when we're talking about Boolean, we usually read that exclamation mark as the word not. And we'll be using it again in another context very soon. So this is the not equal to relational operator. If, after all conversions to the same type, the left-hand side is not equal to the right-hand side, then the not equal to operator will give us a true. So if the two values, left and right, are not equal, then you would get a true out of the not equal to. If they are equal to each other, then not equal to will give you a false. And you probably can figure out what the rest of these do from here. I will go through them though. The greater than operator, notice it's bigger on the left-hand side, and that suggests how this will work. If the left-hand side is a greater value than the right-hand side, then the greater than operator will give you a true value. If they are equal or less than, if the left-hand side is equal or less than, you will get a false out of this operator. Less than reverses that. If the left-hand side is less than the right-hand side, then you'll get a true. All other conditions, equal or greater, will give you a false. Greater than or equal to includes the equal case in the trueness when you're doing a greater than comparison. Less than or equal to does something similar. So you'll see, equal to requires two equal signs. A very common mistake is to use only one. All the other operators either stand by themselves or are combined with an equal sign to do their job. And you're probably familiar with them if you've done high school level relational equations before. If not, this might be your first introduction. It might take some practice to remember what exactly each one is. This table is here to help you. Relational operators are used as the first step to turn floats, integers, string positions, and even sometimes two strings into a Boolean value. You can check to see if they're equal to each other, not equal to each other, greater than or less than. In floats and integers, greater than or less than has what you would think is the expected meaning. With strings, is equal to and not equal to expected meanings. Less than or greater than will go by alphabetical ordering, where capital letters are lower in value than lowercase letters. So if you're sorting from least to greatest, capital letters come first and lowercase letters come later. Numbers and symbols also fit into the order. You can look up an ASCII table if you don't know what the order would be. Once you have some Boolean values, you've maybe converted floats or ints into Booleans by comparing them with each other, you can combine trues and falses to create complex questions. And the way you combine them is by using logical operators. There are three logical operators that you need to know about. There's AND. As a logical operator, AND produces a truth table when you combine a left-hand side and a right-hand side. So, if I had two variables, Boolean variables, A and B, and I was combining those with the AND operator, then B could take on the value false, true, and A could take on the value false, which could be combined with a true on B. A could also take on the value true, which should be combined with the value false or true on A. These are the 4 possible states that we would need to worry about when we want to know what AND will do, and they'll help us to build up a truth table. 2 ampersands are used for your AND. That is Shift and 7 on an English keyboard. If both sides of the AND, so I would be putting the AND between the 2 of these, if both sides of the AND are false, then I get a false result. If one or the other side of the AND is false, I will also get a false result. Only if both things being combined by the AND operator are true will I get a true result. AND is only true when both sides of the operation AND are true. And I would typically combine them like this: a left-hand side and a right-hand side. A and B. A double ampersand B. Don't get confused and use a single ampersand. That has a different meaning, and it's a bitwise logical operator instead of a whole value logical operator. It might look like it works right, but there will be some conditions where a single AND will behave very differently than what I just described. The next logical operator is OR. OR will combine 2 values, and anytime there's any truth between those 2 values, the whole expression will become true. This is not to be confused with the English language OR. If I, as an English speaker, were interacting with you, say you were running the till at McDonald's, and you were offering me a healthy salad or fries to go with my burger, you would say, using English OR, would you like fries or a salad with that? As a computer scientist, I could be stupid and I could answer yes, because that is a logically true result. I want one or the other of them, I'm just not telling you which one. The OR that we usually mean in English is what's called the exclusive OR, where we expect someone to only understand this as a logically correct answer if you are choosing one or the other. You can think of this as the either or. Would you like either a fries or a salad? In which case, if I said yes, that would be a bad result. I've said I want both, and that's not allowed. With the logical OR, one or the other or both are allowed. Switching back over to my truth tables, if I was going to do an OR, I would use this double vertical bar symbol. On my keyboard, that symbol is to be found right here above the Enter key. Sometimes it's got a little break in the middle of it. That's okay. It's the same symbol. And you access it by pressing the Shift key down and then pressing down on that key on your keyboard. That is the logical OR. Be careful you don't get the backslash instead when you're trying to use it. If you've got a non-English keyboard, you might have to go and look up where the OR or pipe or vertical bar symbol is located on your keyboard. You need 2 of them. If I was going to use OR, it is a binary operator like AND, and I would write something like A or B to combine A and B using the OR operator. The resulting truth table using the same input values for A and B is false if both A and B are false. In all other situations, if B is true, if A is true, or if both A and B are true, the result of A or B is true. That is the truth table for A or B. There's one final relational operator or logical operator that you need to know about. This is the not Boolean operator. And the not Boolean operator's job is to reverse the value of any one logical or any one Boolean expression. So I'm going to give a couple example truth tables for you here. So if I were to write not A, my resulting truth table would be, looking at the value of A over here, 1. Looking at the value of A over here, true. Looking at the value of A over here, false. Over here, false. I could reverse A or B by wrapping it up in brackets. So I'll continue my truth table a little further. And put an exclamation mark in front of it. That will reverse the truth table of A or B. So I can see what A or B would have been from here, and then I would just flip all of the zeros into ones, all the falses into trues, and all the trues into falses. What we are learning about here is something called Boolean algebra. Boolean algebra is a set of ways to combine trues and falses, and or and not are the simplest Boolean algebra operations. Just like addition, subtraction, multiplication, division for regular algebra or mathematics, the Boolean algebra operations can be used to do very complex things, and they can be combined with each other. They're also either unary. Not is unary. It operates on one thing that comes after it. You can group the thing with brackets so that you have one complicated expression, or you can do it with one single thing. Or and are binary, and they operate on two Boolean values. Those Boolean values could themselves be complex expressions grouped with brackets, or they could be relations that are turning floats or ints into a true or false. You can use brackets to help you to break your expressions down into logical things you want to have happen first or later, or you can rely on the order of operations. So if you are mixing math and Boolean algebra together, this is the precedence of the operators. Anything that's inside of parentheses, inside of brackets, should be done first. What's inside of them will be done according to the order of operations that follows here. Take a quick look here to note that all math operations, multiplying, addition, and subtracting, is higher precedence than all of our comparisons. All of our comparisons are higher precedence than our Boolean expressions or our logical operators. So relations, greater than, less than, equal to, not equal to, higher precedence than and higher precedence than or. And has higher precedence than or if you're combining them. This is difficult at first. Think of it as a special kind of mathematical operation. If one side of an and or one side of an or, by the way, is not already a Boolean, whatever is there will be converted into a Boolean according to the rules set out here. I've said them at the beginning, I'll remind you of them. A non-zero will be coerced to true as a Boolean, and a zero will be coerced to false. I'm now going to switch over to the Boolean practice, and we are going to start applying the stuff that I've covered with you so far. Now, there is an awful lot going on here in the Boolean practice. You are allowed to use the run button. I have one complicated structure that's well ahead of the lab here at the beginning. I've created the custom function called isItTrue. IsItTrue will receive one piece of information and convert it to Boolean if it isn't already. That Boolean value, called E, will then be used in what we're going to learn next, an if-else statement. If the Boolean expression E is true, then this function will print a yes out on the console. Otherwise, else, this will print out a no. This is the general syntax of an if-else statement, by the way. If-else statements expect to find Boolean expressions after the keyword if, and the expression is always wrapped up in a pair of round brackets. The round brackets must immediately follow the if. The true branch of an if always follows the if directly and may optionally have these curly braces. The curly braces allow us to group more than one line of code together. If you leave the curly braces out, you may only have one line of code as the action for the true part of an if. If you wish to do an opposite action to the true action, you may optionally include an else. This else here is the opposite of E being true, so we're going to say no. Okay. Now we've got a little bit of code down below in our main.cpp. We are going to use the isItTrue function to tell us if some Boolean expression that we've created is true or false. We'll see yes if it's true and false if it is not. We've got two examples right off the bat. So we're going to ask, is it true? And we're going to send true in. True should be received by E, and we should see a yes. And then we've got is it true, and we send a false in. The false should reach the else, and we should see a no. And then there's a couple other examples down here. The rest of this example is for us to fill out ourselves and understand. So 42 is a non-zero value. It will be converted to a 1, and I would expect is it true to print a yes. 0 is a 0 value. I would expect that to become a false, and for is it true to print a no. I'm going to press the run button right now, and you can see all of those things happen. So first, line 34, is it true? That's our very first line here in the output. This is true. Yes. Is it true, false? This is false. No. So we're using our if-else expression here to choose between different outputs based on the value of a Boolean inside the brackets that follow. We're going to do something a little more complex. This is just some more coercions. So I'm going to ask another is it true here. Is it true? And I'm going to pass in what is suggested here, the number -11. Before I hit go, you should think to yourself, what is it that's being passed in? It's an integer. What is its value? It is -11. I know it's going to be converted into a Boolean. What is the rule that's going to be applied here? It's a non-zero. I expect to see, for number 3, true. How about pi? Is it true? What is pi? Pi is 3.14159.6, something like that. Pi is usually expressed as a float or a double. It is non-zero. I would expect this to also be true. I'm now going to ask something very ridiculous. Is it true? CS110. This is a string now. Is CS110 true? I also don't know why this is telling me. Implicit conversion from double to bool changes. Hey, it's actually telling me it's going to be true. I'm getting a warning. It's not an error, just a little warning there in the code. I'm going to try running this again now with all of these. -11, non-zero, I expect it to be true. The warning is telling me that this float will be true. And true. Is CS110 true? We will find out when I press run. Okay. So, we've got more of these. Is -11 true? Yes, because it's non-zero. Is pi true? Yes, it's a float, but it is non-zero, therefore it is true. Is CS110 true? Well, it's a string, and it's not a non-existent string, so it's not 0. It's true. In fact, a string with nothing in it will probably still be true. The floating point value, 0.0, is likely to be false, as is the integer, as you saw before, 0. So is 0.0 and is nothing true. So I'm doing a little play here. Is 0.0 true? No, because it's equivalent to 0. Just like integer 0 is equivalent to 0. You have to be very careful when you're building Boolean expressions that you don't accidentally take a regular number and use it with and or or. If you take a regular number and use it directly with and or, it will be converted directly to Boolean according to the rules we've just seen here. Regular numbers, integers, floats, strings, need to be compared with something else to be turned into true or false in a more flexible way. I'm going to undo a little bit to return this to what it should have been with pi and CS110. Let's look at the next part here. Now that I've explained the need for relational operators, let's get some trues or falses out of them. To help me with this example, I've got some integers, I, j, and k. The I is valued 3, j is valued 2, and k is valued 7. I've also got some floats. X is valued 3, y is valued 2.2, and z is valued 7.7. So we're going to ask first the question, is I, with value 3, equal to x, with also value 3? Coercion will happen to make both I and x be the same data type. We usually move up to the most expressive type, so I expect that I will become a float that is valued 3 and then compared against x, and I will probably get a true because they are the same value. Let's try it. Actually, you can see that happening already. Is 3 equal to 3? And it says yes. If I wanted to see that with some floating point formatting so I can see clearly that there's a float in those, I could use fixed, as you learned in a previous lab. And I'd also want to include iomanip if I wanted to change the number of places. So I'm only going to show one place. That'll let us know something is float. So is 3 equal to 3.0? Yes, as far as this is concerned. If there's a minor difference, like 3.0000001, that won't be the same, even though I can't visibly see the difference on the screen. So up to a certain point, floats will remember very small differences that you might not be seeing printed out. Go back to having that as pure 3. Our next question. Is 6, is I, 3, equal to x? We've already done that one, my bad. 7, is j equal to y? That's being expressed over here is 2 equal to 2.2. And I think you can already guess what that would be. Is it true? And that is supposed to be j equal to y. J, 2 equal signs y. Is 2 equal to y? Is 2 equal to 2.2? No. It's very important, as I said earlier, not to make the mistake of using only one equal sign. Only one equal sign is an assignment. What that will do is it will make j become equal to y. And then the value of the expression will be the end result of j, which is 2, which is not 0, which is true. So by removing the one equal sign, I've completely broken this Boolean expression. We'll go on to say here then that 2 is equal to 2.2. Oops. So make sure that you use 2 equal signs if you tend to compare, and use 1 equal sign if you intend to assign or change the value of an operation. Let's next do, is j greater than k? Those are both integers, same type. Is j greater than k? That is 2 less than 7? I think you can guess what that would be, and I would write it like this. Is it true? J greater than k. Is it true? J greater than k. Looking at number 8 over here, I'm going to hit run. Is 2 greater than 7? No. Is j less than k? That's again, is 2 less than 7? And in this case, I would expect it to be true. Is it true? J less than k. In this case, I'm expecting yes. Yes, 2 is less than 7. That's number 9. Now, let's take a look at is j less than or equal to 2. I'm going to have to spell out the 2 myself. Is it true? J less less than or equal to 2. We can see that j is valued 2 over here. It is not less than 2 then, but it is equal. We're including the equal case in this comparison. I expect this one to be true. So we're looking at number 10. Number 10, is 2 less than or equal to 2? Yes. Let's switch that to simply less than. Is j less than 2? I'll remove the equal here from my operation and run it. J, being 2, is not less than 2, and so I would get a false out of that. Is 2 less than 2? No. I'm going to put it back to what the original question asked. Is j less than or equal to 2? And in this case, yes, it is less than or equal, specifically equal to 2. Floating point numbers are often approximate. Is y less than or equal to 2.2? Let's try this one here. There are some tips you need to be aware of. Is it true? Y less than or equal to 2.2. What is the value of y? The value of y is written up here as 2.2, and it's being stored in a float. We're comparing y against 2.2 written raw by itself. Unfortunately, when we write a number like this, it's not being expressed as a float. And there are many times when the float representation of a number is subtly different than the double representation of a number, which is what we're getting here. I'm going to run this. Take a look at number 11. I've asked, is 2.2 less than or equal to 2.2? I'm expecting it to be exactly equal. Is 2.2 less than or equal to 2.2? The computer strangely answers, nope. And I can ask, is it equal to 2.2? And I'll also get, nope. There is imprecision in the representation of floating point values. Doubles and floats are slightly different from each other. And if you're doing several steps of mathematics before coming to an answer, getting exact equality is often not possible. What you think should be equal will be slightly off, and you'll get no's to exactly equals. So we usually allow a little range around something called an error when we're doing our comparisons. So the problem here is that 2.2 is expressing a double, more precise than a y, and 2.2 cannot be represented precisely by any float, double, or anything. If I add a little f to the end, as suggested here, then what I'm writing is 2.2 as a float equal to y, the float, that is also trying to hold 2.2. I'll run it again, and this should become yes, as you might have expected in the first place. Okay, so is 2.2 less than or equal to 2.2? Yes, this is now correct. Now, we've learned a little bit about our relational operators. You should be beginning to become comfortable with equal to, greater than, less than. Do we have any not equal to in here? No, but remember to change one of these. You add a not, or replace the first equal sign with an exclamation mark. And that would change the meaning of the thing to not equal to. I just changed number 7. Take a look over here at number 7. Is 2 equal to 2.2? It's saying no, but I've changed it now to is 2 not equal to 2.2. The logical operator being used is not equal. This will flip into being a yes. Is 2 not equal to 2.2? Yes, it is not equal. I hope we're all doing okay. You can hear me and understand what I'm talking about so far in the video. I've been going for a long time. I've found with the years that I just keep going longer and longer. I must be getting old. Here's some more logical operators. I'm going to keep going. We are now going to be combining relations, like less than, with each other. This is an example of deciding if k is between two different numbers, including the endpoints. Some people are tempted when they are asked to see if something is between two numbers to write the expression like this. Is k between 5 and 11? Is k greater than or equal to 5? And is that less than or equal to 11? What is the value of k again? The value of k is 7. The way that a computer scientist would look at this in C++ is they would first look at this and solve this as a binary operation. Is 5 less than or equal to k? That would be true and would give us the value 1. Is 1 less than 11? That is true. And so you would get true for this operation. It looks like 12 is being asked correctly then. Is 7 between 5 and 11? I'm going to change this subtly. Is minus 100 between 5 and 11? I'm going to replace k here with minus 100. You can see how wrong this way of doing things is. Looking at this from a math perspective, I would expect this to be false. No, minus 100 is not between 5 and 11. However, I will get true. This is step 12, and step 12 is minus 100 between 5 and 11 inclusive? Yes. The correct way to construct this is to compare both endpoints independently and then combine them. In this case, I want it to be true both that the middle is larger than the minimum in my range and also smaller than the maximum in my range. So I rewrite this with an and in the middle. Both conditions must be true. And I have to restate both end conditions thoroughly. So here I'm checking against the minimum part of my range. Is the value I'm interested in greater than the minimum? And is the value I'm interested in also less than my maximum? If it is, then I'm in range. I'll run this with 100. So looking at 12, is minus 100 between 5 and 11 inclusive? No. Before, when I tried to write this more simply with minus 100 in the middle, I got the wrong answer. C++ doesn't understand that kind of range check. Unfortunately, it only understands binary relations, and it can only combine Booleans with and. So you get interesting things happening. I'm going to try this again with k, which is what was in the middle before. And run it. We are back to having this one here be correct. Is 7 between 5 and 11 inclusive? Yes. I'm going to modify the value of k up here. K is going to become 700. It's now too large. So I would expect this to become no over here for step 12. Is 700 between 5 and 11 inclusive? No. Restoring it to its original value of 7. Is 7 between 5 and 11 inclusive? Yes. Yes, it is. So that's one way you could do an inbounds range check. Let's try another one. Is y between x and z? Is it true? Is it between x and z? This is non-inclusive, so I'm not going to include equals on the endpoints. X is my lower bound, z is my upper bound, and I'm going to check y against both of them. Is x less than y, and is y less than z? Now this could be written in different orders, but I like it to be this way, with the thing I want to see is inside the range being sandwiched in the middle. So it's almost like what you want to do in algebra class. So what is the value of y, and is it between those two? The value of y is 2.2, x is 3, and z is 7.7. So I expect this to be false. Let's take a look at what it shows when I run it. 13. Is 2.2 between 3.0 and 7.7? No. So it's doing this correctly. If I had accidentally written this the way that I would be tempted to, is y between x and z, I would have the same problem I showed you before. It unfortunately tells me that 2.2 is between 3.0 and 7.7. Don't be caught with this mistake. Is z outside the range between x and y. So there's a couple different ways I could express this. I know how to say if I'm inside a range. How do I decide if I'm outside of the range? Is it true? And what I'm going to do here is I'm going to construct one of the ones I know how to do, and I'm going to flip its truthness around with not. So not one of the things that we know how to do. So is z outside the range? Z will go in the middle. X is less than z. And x, sorry, yes, and z is less than y. So we're checking to see if z is between x and y. Z is sandwiched in the middle. And then we're flipping it around to see if z is outside. If it was outside before, we would have got a no, but now we're going to flip that no into a yes. What is the value of z? The value of z is 7.7. X and y are 2 and 3. So we're asking, is 7.7 outside of the range 2.2 and 3? The answer should be yes. Let's see if it is yes. So looking at 14, is 7.7 outside the range between 3.0 and 2.2? We're getting yes. Let's mess around with our z value a little bit. So I don't have to scroll up. I'm going to make z become 1. 1 is also outside the range. Is 1 outside the range between 3.0 and 2.2? Yes. How about 2.3? That's inside the range. Not 1.3, 2.3. That's inside the range given here. Is 2.3 outside the range between 3.0 and 2.2? It is still telling us yes. And the reason for this is I did not consider whether x or y were smaller or larger than each other. I've created a logical impossibility. Y is the smaller value, and x is the larger. I need to know if I am bigger than the smaller value and smaller than the larger value in this case. The variables being used here obscure things a little bit. So now, is 2.3 outside the range between 3.0 and 2.2? Nope, it is not. I'm going to change the value so it's smaller. 1.3. 1.3, yes, is outside the range between 3.0 and 2.2. And so is 9.3. There's a few more correct constructions. Moving on then, past 14 and on to 15. Is x smaller than both y and z? So this is not an in range or out of range. I want to know if something is smaller than two other values. A lot of people, when they first approach a problem like this, are tempted to compare x against a list of values. Is x smaller than y and z? This is what the question is asking. Is x smaller than both y and z? X smaller, y, and z. That's translating the English directly into code. But it doesn't work like that. And I'm going to go to my piece of paper here now to show you why. There's an order of operations we need to consider. We have asked the question, x smaller, y, and z. Now, what's going to happen is all comparisons have higher precedence than and or. So we're going to do this comparison here first. So we'll get either a 1 or a 0 out of that, depending on whether x is smaller or larger or equal to y. We'll get one of these two answers. And then we've got an and. Okay? And z over here. Z is unlikely to be 0, but it could be 1 or 0. All we're asking is 1 and 0, or left and right. So if I had put the number for x as 2, and I had put y as 3, and I had put z as minus 1,000, this problem would be solved as follows. 2 is less than 3. That's true. Minus 1,000 is not 0. True. The end result is true. 2 is not less than 3 and minus 1,000. Minus 1,000 is the smaller. The way we should correctly construct this is like this. You fully compare each pair of things. So if I want to know if x is smaller than both y and also z, I say, is x smaller than y? Is x smaller than z? And then I combine them appropriately, in this case with and. So now, if I have 2 and 3, and 2 and minus 1,000, this will solve as 2 is less than 3. 1. True. And then 2 is not less than minus 1,000. 0. False. And then I combine those with and. There's a 1 and a 0. I get a 0 as my result, or a false. So 2 was not less than both 3 and minus 1,000. This is the right way to compare x against two other values. This is the wrong way. Don't do this. And is not a list. So I'm going to fix my mistake here, right? 15, then I run it, is probably going to give what looks at first the right answer. Is 3.0 smaller than both 2.2 and 9.3, right? But it is going to have some subtle mistakes in it. The correct way to phrase this is x less than y and x less than z. Then for any value of x, y, and z, this will come out correctly in C++. Next, is y smaller than any of x and z? Now let's take a look at what we got for those. Is 3 smaller than both 2 and 9.3, sorry, is 2.2 smaller than any of 3.0 and 9.3? For this one here, both do not need to be true. Instead of less than, is y smaller than x. We're going to combine them with or. We only care if one or the other is true. Y smaller than z. I'm on line 16. 2.2 smaller than any of 3.0 and 9.3. Yes, it is. Is 3.0 smaller than both 2.2 and 9.3? No, it isn't. We're good. So this is how you would see if something matches any of a set of conditions, and this is how you check to see if something matches all of a set of conditions. Let's look at a couple more elaborate examples. You will need these for your exercise today. You will need to have a menu in your exercise. Exercise 2 specifically has a menu in it. You're going to be typing in letters like capital C, capital F, lowercase c, and lowercase f, and you need to correctly decide what kind of conversions to do. You also need to correctly decide if you have been given a valid thing to convert. So we're only going to accept F's and C's. If a person types something other than an F and a C, we need to say, no, that's wrong. Don't use that. If they type a D, for example, here, you should not be asked for a number, and you should be said, that's a wrong letter. So we need a test after they type a letter for this question that will decide if they've typed a correct option. In our little example here, in our extra, we have something that can decide if an option O is in fact one of 3 possible valid options, A, B, or C. Right now it is Z. So is Z equal to A? That should be no, false. Or is Z equal to B? That should be no, false. Is Z equal to C? That should also be no or false. And if we look over here, number 17, Z is not one of A, B, or C. No, false. Let's try something else. I'm going to match one of those. I'll make O become an A. That should be true over here. It doesn't match B or C, but I only care if it matches any one of them. I'm going to use OR here to combine them all, those vertical bars. Okay, so is A one of A, B, or C? Yes. Once again, people become tempted to treat the OR operator like some kind of a list. This is not the right way to restate the question in math. Is it true O is equal to A, or B, or C? What will happen here is B is non-zero, therefore it is true. C is non-zero, therefore it is true. And it doesn't matter what we've got over here. This could be true or false. The other two are true and they're combined with OR. Something in here is true, therefore this will always be true. So for now, we would expect it to be true. O is A, and that matches this thing over here. Take a look. Is A one of A, B, or C? Yes. Let's go back to using Z like we had before. Z is not A, or B, or C. But because B and C are both true and are being combined with everything else with ORs, the whole thing becomes true. So is Z one of A, B, or C? We get the result yes. Paradoxically wrong. Once again, we have to complete each side of an or an and with correct Boolean expressions that convert what we're checking fully into Boolean. The coercion doesn't always work in our favor. So is O equal to B? Is O equal to C? We fully compared. Is O an A? Or is O a B? Or is O a C? If any one of those are true, then we'll get a true. In this case, none of those are true because O is a Z, and we will correctly say that Z is not one of A, B, or C. No, it is not. Let's try the next one. Is O not one of A, B, or C? Now, when I was asked a question like this before, I just took something I knew how to do and I reversed it by putting a not in front of it. This time, I'm going to try and express it differently. Is it true? So I know that I need to compare O against A, B, or C, but I want to know if it is not any of them, which means it needs to not be A, and it needs to not be B, and it needs to not be C. All three situations needs to be correct, even though the English here uses or in its list. You need to combine them with and. So the correct way to do this one is O not equal to A. And O not equal to B. And O not equal to C. Darn it, C. Okay, so O being Z is not equal to any of these options. This is the correct test for doing something like that when I run it. Is Z not one of A, B, or C? Yes, it is not any of them. So if I switch this over to an A, O is now an A. It is a match on this one. So it is false that O is not equal to A. We have one false in this long chain of ands, so the whole chain of ands will become a false. Therefore, I will print no. A is A. So it is not none of them. No. Same would go for B. And same would go for C. Okay. I'm going to switch back over to Z. And finally, try a different method than before. Is O not one of A, B, or C? I'm going to go back to using the exclamation mark method that I rejected at first. So to use the exclamation mark method, I would start off with something where I can decide something is one of a set. And I can reverse the whole thing. I wrap it all up in brackets. and I put an exclamation mark in front of it. So I have reversed the thing that decided if something was one of the options and turned it into something is not one of the options. Some people have an easier time constructing a positive statement using logic than a negative statement. So don't be afraid to flip. I'm going to hit run. So both 18 and 19 should be equivalent to each other in all cases. And you can try that for yourself. So this is very useful to you in exercise number 2. In exercise number 2, you're going to have to distinguish between F's and C's, lowercase and uppercase. You'll also have to distinguish between legal conversions and illegal conversions. After a person types a letter, you need to look at the letter and decide if it's an F, capital, lowercase, C, capital or lowercase, and then only do all of this work here of getting a temperature to convert, converting it, and printing out the result. Only if it's an F or a C of some kind. If it's anything else, you would need to print wrong option. So you'll need to correctly use if-elses to decide whether or not to do the code I've highlighted here. You also need to correctly convert Celsius to Fahrenheit on all C's, not just capital C's, which is what this code will currently do. We'll only perform this calculation right here in the case of a capital C, but it should also be converted. That calculation should happen in the case of a lowercase c. So you'll have to add some options here. You'll have to add an if over there. In exercise 1, you're going to be writing a code that can decide which of 3 integer numbers is the smallest. You'll need to compare one number against the other 2 possibilities. And if it is less than or perhaps equal to the other 2 possibilities, it is the smallest. Let's take a look at if-else statements in a little more detail. Now that I spent a long time on Boolean expressions, we won't have any trouble understanding them when they are put here into an if statement. An if statement allows us to make choices. If a Boolean expression wrapped up in brackets is true, then we will conditionally do code that follows. If you use curly braces, then all of the code in the curly braces will only run if the Boolean expression is true. If you leave the curly braces out, then one line ending with a semicolon will run. We have a simple example here. Int number sum. We've declared some variables. We set sum is equal to 10. We ask, please enter an integer value, and a person is able to type in a number. Whatever they type will be the value for number. We know that sum is 10. If the number is less than 0, then we set the number equal to 0. And then we add that number onto our sum and print out a result. So what should happen is if I type in any negative number, the sum will not change. But if I type a positive number, the sum will change. So I'm going to go back to our lab notes. I'm going to go into lab 5, and I'm going to do a demonstration run of this project. Now you'll notice that we did not give you a complete program. Increasingly across the semester, we will be giving you less and less code. So you need to be very comfortable with doing all of the basic stuff of setting up a program if you want to run our examples. Notice that every time I open a curly brace, I indent by 1 level. Same thing is true for if statements. This number equals 0 is indented by 1 level, or at least it should be. I think it's actually indented a couple levels. So this program here, I think, has declared all of its variables. It's initialized them. I should be ready to go on it. I will compile demo.cpp. Please enter an integer value. 5. 5 in this case is not less than 0. Therefore, 5 will be added onto the sum. Number will not be reset to 0. And I expect the answer 15. If I run it again, and I type in minus 5 is less than 0. It will be reset to 0, and I will not subtract 5 from 10 to get the answer 5. I will instead print 10. So that's an example of a Boolean expression being used to control whether or not a line of code will occur. I could reverse this. I could switch this to be greater than 0. If a number is greater than 0, then I will switch it to being 0. I'll now recompile the program and run it once. We'll try again with 5. In this case, 5 was greater than 0. It got reset to 0 and had no impact on the sum. If I were to choose -9, that is less than 0. And 9 is subtracted from 10 to get the correct sum of 1. So that's our first example. A Boolean expression is being used to decide whether the following block or line of code will or will not run. So long as the expression is true, the block that follows will run. Our next example is an if-else statement. If-else statements are like if statements. At first, they have a Boolean expression. If that Boolean expression is true, then you run the block of code that follows immediately. Be careful not to throw extra lines between the opening and between the if and the opening curly brace. And then there's an else that can follow. The else will run if there is a false. Be careful not to have any extra lines after this brace before the else, or they won't match. Basically, if Boolean expression must be followed directly by a brace or one line of code only for the true condition. And the else, if it's going to match with the if, there can't be more than one line of code or any extra lines outside of curly braces, or the else won't match. I'll give you an example here in a minute of what I mean. So we've got our if, we've got our else. If the Boolean expression is true, we run the block that follows the if. If the expression is not true, we will run the block that follows the else. We've got a little example here that works with some ages. We're going to get very ageist and maybe slightly sexist here. I am terribly sorry. These examples are old. I'm going to throw away the code I had before. And you'll notice this example is kind of incomplete. It doesn't have everything that we need. It assumes that there is some variable called age that we're interested in. I would like to be able to provide different ages, so I'm going to prompt, how old are you? And I'm going to read into age. I've chosen int for age because most people don't refer to themselves as 5.7 years old. They usually give a whole number and round down. I knew a person who always rounded up. She was very concerned about seeming older than she was. Very, very odd. I'd never encountered that before. Wanted to be mature. Anyhow, how old are you? Type in whatever age floats your boat, and this will do an if-else and decide if you are a senior or not a senior using the old cutoff of 65. How old are you? I am 64. You are not a senior citizen. Thank you. How old are you? I'm going to test the boundary. I've got this value I'm comparing the age to of 65 right here, and I'm interested in how this logical operator will behave. 65. 65 matches this. The age is part of the equal part of this relation. So I am actually 65. It will go down the true path here and not the false path and print not a senior. And anything higher than that, of course, you would expect to be a senior. All right, now I'm going to do a little extra cout right here. I would like to put exclamation marks every time I meet a senior. And I'm doing it as a second line. You can see immediately that I've got a problem. This if-else statement here has flagged that the else doesn't match anything. It's expecting some expression. It's expecting that else will always follow an if. The thing I've done wrong is I have two lines right here that are not grouped together using curly braces. So I should correctly write this like this. If I want to do two lines of code in response to an if or in response to an else, I should group them together with curly brackets. I almost always write my if-elses with curly brackets as a result, so that I never forget to put them in. It's also a problem if you have a single line, even if it's just a semicolon between a curly bracket at the end of an if and the else that is supposed to follow it. So do be careful. I'm going to recompile this and run it. How old are you? I am 12. You are not a senior citizen. How old are you? 66. You are a senior citizen. Wonderful. So that's how if-else works. You choose one optional branch of code or the other one. With an if-else, you'll always do one or the other based on the trueness or falseness of the Boolean expression. So constructing a correct Boolean expression is important to make sure you get the right path through your code. Any if can have an if-else or an if put inside of it. Any else can have also an if-else put inside of it. And our later examples will show that that can be done. I am not going to run these examples here. These are just more examples of combining things using and. So we could, in theory, add a gender variable and let people type in whatever they like. And if we happen to have someone that is over 65, a senior citizen, and also they've represented their gender as F, whatever that is, they'll be invited out to quilting group. Isn't that nice? This also has a little warning about using curly braces to group together many lines of code. And this produces the same error I tried to show you where you have an else at the end and there might be a syntax error. So you can take a look at this on your own and see if you can make it work and invite different types of people, age ranges and gender options to your quilting group. Nested if statements is next. We're going to expand our age example by adding in more age ranges. So what we're doing here, I don't like this code, so I'm not going to copy paste it, but we are saying if your age is greater than 65, we'll print out a senior. Otherwise, we're going to go and the else will have a complicated if-else structure inside of it. So if we were not over 65, we'll check maybe we were 19, greater than or equal to 19 and an adult. If we weren't that, then we'll have another else, and inside of that else, we'll have another if-else. I prefer that this be expressed using full curly bracketing or using another method that I'll show you in a moment. So here's the same thing as before, done with curly braces. Of course, it doesn't matter what your age is, you're a great person. And I want all of that indented one level. All right, so we're going to ask how old you are as before. You are, if you're more than 65, a senior. Otherwise, if you're more than 19, you're an adult. Otherwise, if you're neither 65, you got into the else for 65, and if you're not 19, you got into the else for 19, then we have a choice. You're a teenager or you're a child. In all cases, at the end, outside of all our if-elses, we still say, you're a great person. I'm going to compile and run this, and I'm going to check a few of these boundaries here. Okay, so I want to become the youngest possible adult according to this if-else structure. So I need to fail the senior citizen test. I need to be 64 or younger. Then I'll be able to get into this else, and I want to just barely pass the adult age test. So we're going to include 19 in adult. How old are you? The youngest possible adult. You're a great person, and you're also an adult. The oldest possible teenager is one less than the youngest possible adult in this example. So if I said 18 in this case, I would have had a false response to here and ended up in this else. And if I say 18, that is greater than or equal to 13. Notice we're excluding previous ages as we go deeper and deeper. 18 is a teenager. 13 would also be a teenager. And strangely, minus 200 years old will be considered a child by this system because we have no other options after this. Funny, isn't it? How old are you? Minus 200. You are a child. You are a great person. No, you're from the future and you're a time traveler. Or, even worse, you're probably a liar. Let's not worry about all of that too much. Instead, we are going to worry about it. I would like to eliminate people that are giving me bad ages and call them out on it. I'm going to combine stuff. I'm going to do the age range check stuff I was talking about before to take a look at my ages. So after a person tells me, how old are you? I'll throw in an additional if. If your age is greater than, what's a really old age? I don't think people are going to be. I'll say 200. Science is going to let us live to be 200, but probably not much more. I don't even know if it'll get there. But if somebody gives me more than 200, I'm going to call them a liar. Okay? So if the age is greater than 200, you're a liar. What's another age that might be a lie? Age less than 0. I don't think time travel of this type is possible. I don't think we'll ever have somebody visit us before they were born. So age less than 0, I'm pretty confident we can get rid of that. How do I combine these? I've kind of written them out of order. I need both of these to be true at the same time if I want to start looking at people's ages. So I need them to be not less than 200. I need them to be less than 200 and more than 0. So I'm doing what looks like a negative check at first. If I notice their age is more than 200, or I notice their age is less than 0, then I know I've met a liar. Aha. Otherwise, else, all the rest of this program is going to get grouped together as what I do with people who aren't lying with me about their age. And I include being a great person in not being a liar. Okay, so if they've told me an age that's too big or they told me an age that's too small, I call them a liar. Otherwise, I do everything from this opening bracket all the way down to this other one down here that matches. Notice that if I click on a bracket, the matching closing one highlights as well. So I know where the beginning and the ending of this else is. It's quite long. You'll need to do something like this in your exercise too. You are going to be checking to see if a letter is one of the valid options. And if it is a valid option, you do all of the highlighted code here. You'll have brackets around that if it's a true option. If it's a false option, if it's not one of those valid options, you'll say wrong letter. It's very similar to what I'm doing, but you'll have to check to see if something's one of a list of options instead of out of bounds. Okay, so I've dealt with being out of bounds here, and if you're not out of bounds, then we can do all of the cool action of categorizing again. So let's try that previous example. Compile the demo.cpp, and I'm going to run this. How old are you? Minus 200. You are a liar. Fabulous. Okay. How about 1,000? I truly am 1,000. I'm an elf. I've got pointy ears, and you can see my Dalish bow over here from a certain Canadian video game. You can't see it, actually. I'm sorry. No, it's calling me a liar. The upper cutoff for truthiness in age is 200, so that's a liar. Did I break the rest of the program? Is it just always going to call me a liar? How old are you? I am
3 years old. You're a great person and you're a child. Yay!
Okay, and how about if I'm 14? You're a teenager. You're a great person. Everything else seems to be working. How about that senior citizen cutoff? 65 years old. You are a senior. You are a great person. How about 200? Still says a great person. That's the upper boundary. We are only calling a person a liar the moment they go over 200. So I'll go to 201. 201, you are a liar. Okay. Now I can express this in reverse as well. The rules for reversing these things here, you can either wrap it up in brackets and put an exclamation mark in front, or if you need to reverse something truly, you take every relation and you replace it with its exact opposite. So instead of greater than, I've got less than or equal to. Instead of less than, I'll have greater than or equal to. And instead of or, I'll have and. So now anytime a person gives me an exact age, a correct age, I'll be calling them a liar. And if they're out of bounds, I will have problems. Let's see what happens. It's fun. Okay, I am 45. You're a liar. What? I am 201. You are a senior. You are a great person. I am 0. You are a liar. I am -1. You are a child. You are a great person. I need to reverse the actions I'm doing. I'm doing the you are a liar option if a person's age is in bounds. So I need to take that out here, and I need to turn the you are a liar into the else in this case. So the order of the code kind of depends on how you structured your Boolean expression. Now, when I typed else, you might have noticed it tried to give me an else if. I'm going to get to that in just a second. Compile. And we'll just double check with an adult. 23. And me. You are an adult. You are a great person. We're back to behaving properly. I'm going to try something that's very small. You're a liar at -10. All good. All right. So. This thing that's happening here, where I've got lots of brackets and things get nested deeper and deeper and the tab gets deeper and deeper, programmers don't like that. It gets hard to read. So if you have a bunch of options where one eliminates some stuff and then the next one tests to see what's possible with what's left over, you've got a whole bunch of exclusive options being tested one after another, those can be simplified into something called an else if. So you just get rid of the curly brackets for the nest, and you just use else if over and over again. And then I've got these extra curly brackets down here that I don't need, and I'm going to fix the whole thing up. Oops, I don't know why that didn't line up nice. There we go. So in this case, I'm saying if the age is greater than 65, we'll say they're a senior. Else, if the age is greater than 19, we'll call them an adult. So if we didn't match this rule here, we're going to check the next one right away. And then we'll check the next one. And then we'll check the next one. And so on. In the lab notes, we have another example of an else if, down at the end. Way down here. We've got grades. If a grade is an A, we can say great work. Else, if it's a B, we can say good work. Else, if it's a C, we can say passing work. Else, if a grade is a D or an F, we've got a couple lines here and therefore some curly brackets. Unsatisfactory work, see your instructor. And finally, if you want, you can have an else to catch all the things your previous checks didn't catch and have one more thing. Not a legal grade in this case, if it's not A, B, C, D, or F. Okay. So to review, in exercise 1, we are going to have you prompt for and read 3 numbers. Notice they're supposed to be integer numbers. You will then use something like maybe an if, else, to print out which of those numbers is smallest. You should compare the first number against the other two and see if it's smaller than both of them. If it is smaller than both of them, you can print it. If it is not smaller than both of them, or maybe equal to both of them, right? Smaller than or equal to, smaller than or equal to. If it is smaller than or equal to, print it. If it's not one of those things, move on. Then there are only 2 numbers left. You don't have to worry about the first one anymore. You've eliminated the possibility. Are the next 2 numbers? Is the second number smaller than the third number? If the second number is smaller than the third number, you print the second number. Finally, there's only one possibility left. The third number must have been the smallest. You can print it. There's an idea of how you can do this exercise. For exercise 2, I've given you some hints already several times, but to summarize, after a person types in their letter option, you need to check to see if it's a F, capital or lowercase, a C, capital or lowercase. If it is one of those, go ahead and ask for a temperature, perform a conversion, and print the converted result. If it is not one of those, you'll print wrong letter. This calculation here is being limited to just capital C's. If you run through the sample test at first, you'll notice that capital C gives one result and capital F gives another one, but lowercase c and lowercase f always give the same result. So you have to add in more options to do this calculation here for capital C and lowercase c. Because there's only C's and F's possible, the only thing that could reach this else is F's. You don't need to add an else if here if you don't want to. Okay. I'm going to stop my recording. This went on a lot longer than I thought it was going to, at 1 hour and 21 minutes, but it's because I took a long excursion into Boolean expressions.